Why time slows down near light speed. Einstein's special relativity predicts something incredible. The faster you move through space, the slower you move through time. This is time dilation, and it's not just theory. GPS satellites correct for it every day. Let's understand this with a thought experiment. Imagine a clock made of two mirrors with a photon bouncing between them. Each bounce is one tick. This is called a light clock, and it works the same way for everyone. Now, what happens when this clock starts moving? Alice is standing still, watching her clock. Bob is moving past her at high speed, with his own identical clock. They both start at the same time. From Alice's perspective, Bob's photon has to travel a longer path. Instead of just going straight up and down, it travels diagonally as Bob moves forward. Think about it like throwing a ball straight up in a moving car. From outside, the ball follows a diagonal path. But here's the key insight. Light always travels at the same speed. It doesn't matter if you're moving or standing still. This was Einstein's great discovery, and it changes everything we know about time. Since Bob's photon travels a longer path at the same speed, it takes more time to complete each tick. This means Bob's clock runs slower than Alice's. Time itself is passing differently for them. This is time dilation. The formula is elegant and profound. T prime equals t divided by the square root of 1 minus v squared over c squared. Let me break this down. T prime is the time experienced by the moving observer. That's Bob's time. T is the time experienced by the stationary observer. That's Alice's time. V is the velocity of the moving observer. And c is the speed of light, approximately 300,000 kilometers per second. The formula shows that as velocity approaches the speed of light, the denominator approaches zero, and time dilation becomes infinite. At light speed, time would stop completely. Let's look at some real examples to see how dramatic this effect is. At 90% of the speed of light, time slows down by a factor of 2.3. That means for every year that passes for a stationary observer, only about 5 months pass for someone traveling at 0.9 c. GPS satellites have to account for time dilation. They orbit at about 14,000 kilometers per hour. Without corrections for both special and general relativity, your GPS location would be wrong by about 10 kilometers every day. The satellite's clocks run slightly slower due to their speed, but slightly faster due to being farther from Earth's gravity. The net effect must be precisely calculated. Muon particles, created when cosmic rays hit our atmosphere, live much longer than expected. They have a half-life of about 2.2 microseconds at rest. But because they travel at 99.5% of the speed of light, we observe them living about 15 times longer. Without time dilation, we wouldn't detect muons at all at ground level. And then there's the famous twin paradox. If one twin travels in a spaceship near light speed for a journey, when they return, they'll be younger than their sibling who stayed home. This isn't science fiction. It's a real consequence of Einstein's physics. The traveling twin literally experiences less time. Time is not absolute. It depends on how fast you're moving. The faster you go, the slower time passes for you relative to someone standing still. That's one of the most mind-bending ideas in all of physics, and it's been confirmed by countless experiments. Einstein showed us that space and time are woven together into a single fabric called spacetime. And the speed you move through space affects how you move through time. This is the foundation of modern physics, and it changed our understanding of the universe forever.